Okay, so so in chapter 1, we revised what vectors and matrices were and what being random was. But now we're going to look at putting those two together, which is absolutely fundamental to all the other things we're going to be doing. So we had a kind of pragmatic approach to both of these. So a bit of notation for length P vectors X and Y. The notation that vector X is less than or equal to vector Y stands for the statement that xi is less than or equal to yi for all I. And then we use this square bracket notation to mean all the integers from 1 to 3. Okay. So we're going to define so a random vector is a length P array of random variables characterized by its distribution function F. Okay, and F is, we're going to subscript it with big X, the random vector, so random vector, big X vector. So this is a subscript and it's evaluated at a value little x. And that is the probability that each element of big X is less than or equal to little x for little x. So the intuition is what I wrote on the board the other day, which is by knowing so that's the X there. So by knowing the probability density here, right, that's enough to specify the random vector, right? Because you can use that to build up. You can use that to build up whatever kinds of volume you want, right, in the space, and see what probabilities are of volumes. Okay. So we'll sometimes omit this subscript, big X, where it's kind of obvious. So we'll sometimes just write F, big F of X. And for continuous variables, so the probability density function or PDF. There's going to be a little of length P. Random with so the distribution function bigger is defined through this equation, which is that the density function, big F of x, is the integral from x prime 1, then from minus infinity to x1, up to the integral of x prime p is minus infinity to xp of f of x prime dx1p to plus dx1 prime to dx p prime. Okay, so that defines probability density functions, multiple integral, like where the, in the same way that for the univariate case, it's defined by a single integral. So let's give an example of that, and this year we're going to get very, very, very familiar with this example. Multivariate normal. Random factor. That's PDF. And we're going to write this like 30n. Yeah. And again, we'll subscript p, but not always. And that has an argument of x, and it has some parameters, mu and sigma. And it's 1 over root 2 pi p times that of sigma times e to the minus a half x minus mu transpose sigma inverse x minus mu. Okay, so what's this quantity here? Is this a scalar or a matrix? So who thinks this is a scalar? Who thinks this is a matrix? So let's work it out. What are these? These are column vectors. So that's a p by 1, that's a p by p, and that's a 1 by p. So when you do the matrix operation, what's going to come out? This whole thing here. You're going to sum over the p, sum over the p, so it's going to be dimension 1. So is it who now thinks it's going to be a matrix? Who now thinks it's a scalar? Yeah, so it's a scalar. So this is what I mean. It's like it's really fiddly. It's not deliberately fiddly. It's just very, very easy to. So the point is that the density maps from. If you think about it, it maps from RP onto R. Yeah. So in general, these apps map from RP to, and they have to be positive actually. So, yeah, in general, right? So you expect it to be a scalar, but there is such a thing as a matrix exponential. So you can get exponential matrices, and you will. Well, when we think about sampling distributions, we'll look at some stuff that's a bit like that. Okay. So what I do now is I write out exactly the same things I've just written, but for matrices. Okay, which is a bit like duplication of effort, but it's worth doing because we'll see it all again, right? So okay, so what we're going to do is we'll say for n by p, say for n by p matrices x double underscore y, yeah, x double underscore y is less than equal to y double underscore y stands for the statement that xij is less than or equal to yij or I in the integers from 1 to n and all j in the integers from 1 to p. Yeah. So definition 2.1, a random matrix X is an N by P array of random variables by its distribution function so F of a matrix evaluated at Y, for a matrix evaluated at Y, equals the probability that X is less than or equal to Y. Yeah. Or Y in R and by P. Right. So I don't really need to write the times because it's just n, it is just n times P. And the and this time the PDF is defined by so that F of the matrix is the integral from x in 1 primes is minus infinity to x11 up to xnp primed is minus infinity to xnp on the PDF of an x primes on the x 1 primed up to dx p primes, yeah. And yeah. One thing one thing that we might start doing, yeah, is writing, we're going to start writing this kind of thing in general like this as a derivative over n by p on all the variables, right? So it should be kind of reasonably obvious what that means. Okay. And the point is, the stuff I said about Dirac deltas before, that's what's going to let us deal with the next thing for mixtures of continuous and discrete variables. But one of the things we're interested in about random vectors and random matrices is their expectations. Yeah. So mean, it's the most fundamental thing we want expectations for. So what I'm going to do now is I'm going to define it for the matrix, right? And the same thing will hold it for the vector if one of the dimensions is 1. Okay. So for a random and by P matrix X. So can you remember what our example of a random n by P matrix was? What did we mean was a random matrix? Data matrix, right? So we're thinking about something that's got n observations, each observation's got P features. Okay. And this is random because we're working in a framework where we think that the data generating process is either noisy, so there's error on the experimental apparatus, or we've sampled a small number from a large population, which leads to some variability in randomness. So that's where the randomness is coming from in this kind of data matrix, right? So for that random matrix, it's mean E of the matrix is n by P matrix with the ijth element of that matrix is equal to the expected value of xij, right? That's the ij element of E of matrix X or vector X, if you know, we follow through in the same way. This is the integral from x11 is minus infinity to infinity up to the integral of x and p prime. Let's check the up is minus infinity to infinity of x ij times f. So times the PDF, right? So you should see this this is starting to generalize the univariate case. Yeah. And because writing out all these dots is just a massive pain, what we can do here is we can simplify by saying, well, actually, it's the integral over Rn by P. Yes, there's NP variables in the matrix of x primes ij weighted by the probability density function over n by p different matrix elements, right? So that's a more compact expression. And then where G is a matrix function that takes us from the original dimensions of our matrix into some other size, yeah. The expectation E of G of X, yeah, is M by Q matrix with ij elements equal to so the expected value of G ij. So the argument is a matrix argument, yeah. And then the thing that it maps onto has I and j things. Again, one of these could be one. And this, I write it out in full in notes, but we're just going to write it in the more compact form. So, first thing to note about this expression is it uses the I've missed out the most important bit on the notes, fortunately, which is for all of these we've assumed that we've got a PDF, so almost everything we're going to deal with. Yeah. Almost everything we're going to deal with is continuous, but if you've got some discrete ones, then you can add Dirac deltas to this, so one of the definitions we're going through, right? So that's why I talked about the Dirac delta, sort of saying we don't really need to worry about some of these things being discrete, because you can just have a spike in them. You can just have a spike in that. And the second is that I've defined this in terms of matrices just because I mean, what I would suggest you do is look at this expression and look at G and X, say you can have scalar vector matrix Yeah, scalar. Then a matrix. So there's a 3 by 3. There's a 3 by 3 grid here. Yeah. And I think we meet pretty much everything in this grid in the course, right? So I'm not going to write out 9 definitions. That's what I'm trying to say. That let's just think about the most general function. But lots of things are going to have there's going to be lots of combinations of things, right? So get used to this general definition and the idea that we're dealing with lots of different kinds of objects. Okay, so has anyone got any questions about that? Those definitions of matrices. All we're thinking about is they're just sets of random variables, and we're taking them in some sort of ordered way in arrays and matrices in tuples and arrays. But what we've not done is assume that you can split that the distribution or density functions. We've not assumed you can split them up, right? So we're allowing these things to depend on each other. And that's the main sort of point, right? That you could always put a load of independent random variables in an array and that will tell you nothing. But we've at no stage assumed that the probabilities, in the sense that we defined independence in chapter 1, we've at no stage assumed that those probabilities involved are independent probabilities. Okay. So let's just give one quick example. So if X is multivariate normal, yeah, then the expected value of X is mu. Yeah. So where does that sit here? Where does that example sit here? I think it's here. Yeah, everything's vector. Yeah, vector G, vector mu. Okay. So now we're going to think about covariance. Okay. And this is what I said about them. These factors aren't necessarily independent. So the covariance of a random vector X is, we're going to write this as cov of X, and this is the expected value of X. X transpose minus the expected value of X times the expected value of X transpose. Yeah. So we get variance back if P equals 1. Yeah. So notes, we recover variance for P equals 1. Yeah. Where does this sit in the XY thing? What's G? So what's X? Sorry, what's X here? Is X a vector or a scalar or a matrix? What do I say X is? Vector, yeah. And so what's G over here? So this one here, G is a matrix, because you're mapping a vector onto an outer product. So not, I mean, it's tricky, but it's not a big trick. questioning that you've got some here and you've got some here, right? Because the e-ax and the t-ax are vector functions, G. Yeah. And they're different g's, right, in each expectation, the g's are different function. Okay, so we've got the variance of p equals 1. And if x is mean mu, then the ij element of cov x is this thing here. So the integral of xi minus mu I xj minus j x. Yeah, so this can be a slightly easier way to think about it. Yeah. Element wise, the ij element of the covariance is xi minus mu I times x mu minus mu j, and then expectation of that over x, right? So that's what you do when you take those off, right? You should take them off the mean. Okay. So this would be a slightly easier way of thinking about it. And then if you want an example, if, again, our favourite example, the multivariate normal, x goes like normal sigma, yeah, then of covariance of x is sigma, yeah. So that matrix G in vector. This example here is this one here, it's matrix G in vector. X, right? So I won't keep filling in this table, it's worth saying that I will see all of these. Yeah. Okay. So any questions on that? Any questions on expectation? Correlation and independence. So if x is a length p random vector and y, I want the most pen, I'm doing for some reason I have not managed that. Very slightly very well prepared. These ones in the remark, great. Y is a length q random vector. Yeah. We say x and y are uncorrelated. The expectation of x y transpose is the expectation of the outer product is the outer product of expectations, right? So that generalizes the notion of being uncorrelated for scalar random variables, right? If these reach scalars, yeah, that recovers the idea of being uncorrelated. Yeah. And but correlation is weaker than independence, right? So you'll have seen this classic example in the univariate case, right? You can make a circle like this of points, right? Where that's x and that's y, right? And in this circle, x and y are uncorrelated, right? Which means that if you regressed one against the other, the optimal regression line would be flat, right? They're not correlated, but they're obviously not independent, right? So if you know X, you know something about Y, okay? So correlation is like the linear phenomenon, yeah? But there are other ways to depend that are like not linear, right? And to do with higher order features of the data, yeah? So to catch out that idea, so if we're going to let Z be a vector making concatenating X and Y, yeah, and then F, the distribution function of Z is equal to the distribution function of X times the distribution function of Y, yeah, for all X in R, Y in RQ, little z is X, Y, yeah, or equivalently, yeah, that's if you think about it, that's the same as having the PDFs being the same, yeah. Yeah, close to the same. Then if that holds, we say that X and Y are independent, yeah. Okay. And so note, correlation implies non-independence. Yeah. But independence doesn't imply correlation. Yeah, it's not an if and only if. And if you think about it, the reason this product form is the right definition is if you go back to our definitions of probability, this is, omega is all the things that can happen, right? And what you want to know is what's the probability of this, this is, you're interested in regions like this for the probabilities of R, right? Regions like this for any kind of width for the probabilities of Y, yeah. And the only way you're going to be able to make all of the possible regions that you could make, the only way you're going to make the regions, those events independent of each other in the sense that we met when we were thinking about probability spaces, is it that rule is a product form, right? So we're not going to go through how you show that, but it should sort of be intuitive, right? That if you've got a product, then in the sense that we were talking about with omegas and what happens, right? Those random variables are the events captured by the random variable being equal to something. Yeah. So when we do our probabilities, we have omegas, we have A's in the omega, right? And an A would be something like X falling in this regime, right? And we talked about what it meant for probability independence and so on, right? So you can go through that if it is of interest. Okay. So yeah, but the product form is not the general one, right? And if you think about the multivariate normal, it's the sigma matrix that stops it from being something that you can write as products. Yeah. If you think about the multivariate normal, it's not a product form. It's not a product form because sigma inverse is not a simple matrix. It's a general matrix, right? That's the reason it's okay. That's the reason the multivariate normal captures things that are not independent. Okay, so now I've got my generating function. How does this generalize the univariate case? Well, so the moment generating function, we're going to write as MGF of a length P. Random vector X with the f of f is going to be, so right, a moment generating function M, but this has a subscript and it takes a vector argument T. Yeah. Okay. This is the expected value of e to the T dot X. Yeah. Which is in our more compact integral notation, integral RP of e to the T dot X. So if you think the moment generating function maps from RP onto, again, it has to be positive values, right? On f of X, D, P, yeah. So example, if X is multivariate normal, then M of X at T takes this form, which again you'll see generalizes the univariate case. Yeah. And that's going to be quite a useful form to work with, right? So the reason moment generating functions are useful, and this is now, I think, one of the problems, is that if two things are independent, then the MGF of the sum is the product of the MGFs of the variables that you're summing. Yeah. So that's why. In fact, no, it's not one of the problems. We're going to prove it now. Okay. So where X and Y are length P. So we used this implicitly before when we were proving the univariate central limit theorem, right? So an X and Y are length P, independent random variables. The MGF of their sum is a product of their MGFs, i.e. moment generating function of X plus Y evaluated at t is moment generating function of x at t times moment generating function of y at t. Yeah. So let's think about what m of x plus y is. Well, it's the integral of e to the t on z x plus y on z dz. Yeah, so z's just a useful dummy variable to integrate over, and that's by definition 251. Yeah. So that's the integral over r e dot z on the integral fx of x fy of z minus x. Yeah. Yeah. And so we're allowed to do this from equation 2 or 1, right? And so 2, 4, 1 right. 2, 4, 1 I forgot to label, right? But that is saying that the product is so that's saying that the f of x plus y is the product of f and y, right? So 2, 4, 1 told us that you could write f of the of two things that are independent. You can write their joints. You can write the joint as the sum, yeah, as the product. So, okay. So technically, you should have an independent step where I write f of x, y. You know, I write f as an f x, y. So really, if you want an intermediate, yeah, you could write this as f of x, y, yeah, with the right arguments, yeah. Somehow, yeah, with some sort, yeah. And then it's going to plot that down. Okay. So now we're going to do both of those integrals. We'll pull both of those together. So it's RP e to the t dot z minus x e to the t dot x. Okay, and that's just multiplying and dividing by the same thing. There, yeah, multiplying by e to the tx and dividing by e to the tx on x of x and fy of z minus x. Yeah. dpx dpy. Yeah. And then I noticed that I can pull both of those out to do an R1 integral on e to the t dot x, right? So the e to the t dot x on dt on x of x dx and now I just make a change of variables. Yeah. So I change the variables z minus x to equal y. Yeah. Change the variables. Yeah, and that's then the two definitions. Yeah. So that's definition. Right, and that's what we wanted to show. Okay. So that's why we care about moment generating functions, that when things are independent. And so what can we think of that's independent that we've mapped? What we normally assume, right, is that in the data matrix, yeah, we've got a load of feature vectors. Yeah, and we're normally going to assume that each of these vectors is independent, right? And we'll do things like summing these up to make means, right? So that means that those sums to make means, right, are going to look themselves going to look normal if the population distribution that we sample the feature vectors from is not generic. Okay, so I think we will leave it there for today. Any questions on what we covered today, or anything from chapter 1? Any questions on anything? I mean, so hopefully this recording will work, and I'll be able to upload a recording of me writing, right? I hope. It may not everything works, right? And I think before the podcast, when I said before, somehow the slides didn't record. I have no idea why that didn't happen, but you have all of the notes anyway, so hopefully having the note and we thought it'd be this is how it. Great, okay, so I'll see you all tomorrow for the tutorial. What we'll do in the tutorial tomorrow is finish off problems 1. We probably won't start problems 2 yet.